Hey there, here's a little podcast today on making measurements and understanding the fact that sometimes our measurements might have some uncertainty associated with it and some error. So, how can we use this to our advantage when we make measurements in science class? So, first thing, no matter what we do in science class, you should understand that there's going to be measurements that we need to make, and most often the measurements that we do make are not going to be exactly the same. A lot of times we will collect class data, we will compare each other's numbers to help find what the true value actually is. Because sometimes we can measure the mass of the same item, but we might come up with different answers to that same item. And as a result, all of these different deviations from the actual value of that object, this is the result of error. And so random errors and systematic errors play an important role in science. And if we can identify them, it helps make a more valid experiment. So when we do measuring, when we use lab equipment, if it's an electronic piece of equipment, if it's a handheld piece of equipment, no matter what we use, it doesn't matter how sensitive the item is, it's still going to have some error associated with it. So if you take a look at our electronic balances that we use here at school, on the bottom side there's going to be a number and it says can measure exact to plus or minus zero point zero 0.02 grams of that object being measured. So there is some uncertainty even with an electronic balance. So when we look at errors, there's two types, random and systematic. So what's the difference between random errors? Random errors are always present. These are the errors that you can't really control. We try to control as many variables as possible when we conduct an experiment, but there's always going to be some random error involved. And as a result, we're going to see distribution of measurements away from the normal. So if the red line represents the normal measurements, the green line here represents the distribution with some random error involved. Nonetheless, we're going to see some variability in our data. And so when we look at random errors, we try to minimize as many of those, but sometimes there is some operator errors that can be random. Sometimes changes in experimental conditions. So for instance, if we were to do a lab outside, we can't control every single variable that happens outside. Wind speed, temperature, humidity, those variables can affect your experiment, and those are a result of random errors. One way we can minimize them is to make lots of measurements. Do it repeated. Repeat the experiment over and over and over. Calculating the mean, the statistical mean, will help us understand a little bit better what the actual answer is. And we can also measure what's known as the standard deviation. And this is simply the variation from the mean as a result of the experiment. Systematic errors, hopefully we can reduce them, but systematic errors are the result of the system that we are using to make the measurements. So sometimes we can do the measurements and we will notice that our measurements appear to be accurate, appear to be precise, but it might be the result of some instrument limitation. It could be the result of maybe your eyesight and you can't read the caliper correctly. It might be the electronic device that we're using and it's not calibrated correctly. So there's a variety of reasons that we could have some type of systematic error. So when we use equipment, we want to make sure that we can calibrate it. Maybe if you're using a thermometer, you want to compare it to another thermometer to make sure that they're both reading the same temperature before you begin an experiment. Making sure we're using the best possible techniques. So when you measure volume in a graduated cylinder, sitting it flat on a countertop, making sure you're looking eye level, those are things that can reduce the systematic error involved with the experiment. So no matter what, we're going to see that there is some type of error associated with experimentation. Scientists want to make sure that we are trying to be as precise as possible and that we're collecting accurate experimental data. So how do we know what data is precise and what data is accurate? That's something we can try to eliminate or try to do the best job we can when we are collecting data in class. So if we can identify what the errors are and the significance or the magnitude of their errors, That's something we always want to discuss when we write up the analysis to our lab reports. We want to try to reduce this as much as possible. So by using by using better instruments, creating really good experimental designs, collecting lots of data, repeating your trials, this ultimately makes sure that we have more valid data. So again, we've discussed what validity means, and if we can increase the validity, making our experiment more accurate as a result of the tools that we are using. So no matter how we do an experiment, how precise we are in our measurements, how accurate our equipment actually is, there's going to be some error. But one of the things that can help us understand the error is by using some statistics. We use statistics in science class all the time, and this will help us better understand how agreeable our data actually is. So when we use different measuring tools, we need to understand the limitations of each device. Some are much more precise than others. Most of the tools that we use in class should be fairly accurate. So precision is referring to how reproducible are those measurements. So using a device like a caliper is going to give us a very precise measurement as opposed to using just a metric ruler. When we make measurements, we also want to make sure that we are very accurate, getting as close to the actual measurement as possible, hitting that bullseye every time. Sometimes we're not going to know exactly what the correct answer is, but if we look at other people's data, we should be able to come up with an agreement what the actual measurement should be. So when we do science, we want to make sure that we are accurate and we are precise in our measurements. Sometimes we could end up having measurements that are very precise, so they're consistent, they're close to one another, but they're not very accurate. And this could be the result of a tool that you didn't calibrate properly. This is not a good situation where you are hitting close to the bullseye every single time in your measurement, but you're not very precise. The measurements are not close together. And if you are all over the board being inaccurate, being non-precise, that's going to cause some major problems when you're trying to discuss a lab report. So when you do make measurements, this is something you need to remember. When you make a measurement with any tool in science class, we always want to estimate one digit beyond the smallest marking of that device. So if this ruler measures to the 10th of a centimeter, so this is 26.1, 26.2, 26.3, we know that this measurement is greater than 26.1. So we are going to estimate that last digit to the 100th position. So we're going to measure this to be 26.13. So if one student says this looks like it's 26.14 or 26.12, those are all acceptable answers. So that last digit becomes an estimate, and that helps make your number more precise. So when you do measuring in class, every single measurement that you make must always have units. Very important. If you don't have units on a number, you are going to probably get it wrong on a quiz or a test on a lab. So make sure you put units on all of your numbers. You should always estimate one digit beyond that smallest marking. So look at your device. If it's a manual tool and there's a marking scale on it, always estimate one digit beyond the smallest marking. And the last thing, always use the metric system in science class. Working with increments of 10 makes things much easier when we have to do converting and when we have to make measurements in science class. So all numbers that you measure in science, all numbers that you use electronic equipment and get a value from, all of these measurements are significant. We refer to these as significant figures. Sometimes I call them Sig Figs. So every single lab measurement becomes significant. Once you put that unit on it, it tells us something specific about it. So when you make a measurement and you have a non-zero digit, all non-zero digits are significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9 are significant digits. Zeros, on the other hand, sometimes are significant and sometimes are not. So when we look at significant figures in the rules, zeros placed in the middle of a number, like something you see here, 503 grams, this zero is significant. It's telling us the object had a mass of 503 grams. Leading zeros are nothing more than placeholders. So we measured something with a balance and we ended up finding the mass was 0.0002 grams. These numbers are not significant, they are just placeholders, so we know that there's only one significant digit in this answer. When you have trailing zeros, if they are to the right of a decimal, they are significant. So this zero is significant. This is a middle zero. This is significant. So 305.02 grams, all 5 of those digits are significant. If you had a number like 3,500, only the 3 and the 5 are significant, not the last 2 zeros. So trailing zeros are only significant when they are to the right of the decimal. So here are 12 little practice problems for you to attempt. Write these down in your notes and bring them to class tomorrow, and we'll see how you did identifying how many sig figs are in a number like 2,804. Remember your rules. Middle zeros are always significant. Trailing zeros are not significant. Are these two significant? Great question. We'll see you tomorrow in class.